we're going to show that the subspace topology on Y, with Y being a subset of some other topological space X, is indeed a topology. So to prove that the subspace topology on Y is a topology, there needs to be, we need to verify that the subspace topology satisfies three, I guess, conditions of what it means to be a topology. So let's begin. So here we have X with some topology B. So we want Y to be a subset of X. Right. So the subspace topology, T restricted to Y, it has a definition. So we're just going to define that. So the subspace topology. So this is the notation, and it equals. So what you're going to do is you're going to take open sets in X and intersect them with the set Y. So I'm going to write U intersect Y, where U is open in X. So in other words, U is an element of the topology. So this is the definition for the subspace topology. So the three conditions, I'm not going to write them out explicitly. I'll just do it as we go. So what we're going to do now is check that the subspace topology is a topology. The first thing we check is that both the empty set and Y are elements of the subspace topology. So so we need to check that the empty set is in the topology. Now, since X is a topological space, the empty set is in this topology. Right? So what am I going to write? So not theta. Empty set is an element of the topology. And so when you look at this definition here, U is an element of the topology, and the empty set, we're going to let that be U. So when you take U, so the empty set, and you intersect that with Y, you take that intersection. Any intersection with the empty set is indeed empty. So I'll just write that out. So the empty set intersect with the set Y is empty. So this, we've shown it's in here, right? So the empty set is in here. Good. Now that's the empty set dealt with. Now let's look at the whole set Y itself. So because we know that Y is a subset of X, and we could rewrite Y as X intersect Y. It just gives you back Y. So note I'll just write since y is a subset of x, then y can be written as x intersect y, right? Because we want to get it into this form here. Now, again, because we know X is a topological space, which means that the whole set X is in that topology. So this is in the topology of X, and you could let that be U here. And you take an intersection with Y, right? So I'll just write that out since the set X is in the topology, we get that X must be in this set here. It can be written like that. So X, what do I write, is an element of the subspace topology. Oh, sorry, not X, Y. Good. So we've shown that both the empty set and Y itself are in the topology that we've defined here. So that's kind of the more trivial aspect of meeting these conditions. The second condition is that the topology, the subspace topology in Y, is closed under arbitrary unions. So I'll just write that out here. So what we're going to do, we want to take like some collection of sets in this topology here, and you know they can be indexed in any way. You take a collection, well, it has to be in an arbitrary fashion. Take that collection and then take an arbitrary union of them, and then we want to show that that still fits inside this subspace topology. So we're going to take this collection VI, where I is in some index set, be a collection of sets in the subspace topology. So each of these VIs can be written in this form, right? So each, I guess, VI in the subspace topology can be written as, so VI equals some, we're going to call it UI, as it corresponds to this index, and then you intersect it with set Y. Right? It's in this form. So remember, U was, U here is in the topology on X. So UI, so UI is in the topology on X as well. Right? UI in the topology. So we're just constructing this collection. We want to take arbitrary unions of them. So let's take the union of I over I of all these sets here, VI, all these VIs, And as we've just shown, Vi can be written in that form. So it's Ui intersect with Y. And when we're in this form, we're just going to use some standard results of set theory, some set operations. We get that when you take the union of these intersections, you could take the union of just that bit and then intersect that with the set Y. So this would equal the union of I, the UIs intersecting that whole thing with the set Y. And now we're going to use the fact that the fact that X is a topological space. It has a topology, and what are we going to say? This bit is therefore in the topology on X, right? Because you're taking an arbitrary, some UI in the topology, you're taking their unions, because X is a topological space, those sets here are closed under arbitrary union. So what should I write? So since this topology is closed under arbitrary unions, this whole thing, not the whole thing, this bit, right, is in the topology on X, right? So therefore, now this thing can be written in this kind of form, right? So it's in its form now. So, yeah, so this bit, I'll just copy and paste. Hence this must be in the subspace topology. Good. So, yeah, in other words, the subspace topology is closed under arbitrary unions. I'll just write that. Lowercase is closed under arbitrary. Good. So that's the second part, closure under arbitrary unions. And the third and final part is closed. We want the subspace topology to be closed under finite intersections. So again, we're going to take a collection of sets in the subspace topology, but we're going to make them, there's going to be a finite amount of them. So let Vi, let's say, not Vi, V1, V2, and then you keep going up to some finite amount, n, be a finite collection of sets in the subspace topology. So we want to take the intersection of these, right, and we want to show that it still remains in the subspace topology. So yeah, each of these, because each of them are in the subspace topology, it could be written in this form, right? So again, like in part 2, we have we index them with some I. So I'm going to keep my structure consistent. So each vi in subspace topology can be written as, so you take vi, so we know this already, ui for some So now we're going to do a very similar thing, except we're taking finite intersections. So what should I do? So we're going to take finitely many of these. So I and I, or not I and I anymore, because we want finite amount. This is the way we write it. I equals 1 up to n of these VIs. And each VI is written in this way. So it's going to be I equals 1 up to n of ui intersect y. Again, we're going to be using set theoretic results and move the brackets around a bit. So this is just going to equal the intersection of I equals 1 up to n for each of these ui's and intersect that whole thing with the set y. Now we're going to use the fact that the topology on X is, well, it's a topology, so therefore it's closed under finite intersections, right? So since the topology is closed under finite intersections, and we have that this bit, right? This bit here is in the topology. Up to n of these ui's is in the topology. So now we're looking back at this. This bit here is in the topology, and then therefore this whole expression can be written in this form, and we're happy. So hence I equals 1 up to n ui intersect with y is in the subspace topology. So that is in English we say that the subspace topology is closed under finite intersections. Good. So that's pretty much it. Right? So we've just shown that the subspace topology on Y is indeed a topology because it satisfies the three properties that a topology must have. Right? In the first, second, and third here. I haven't written them down explicitly, but I've basically described them to you anyway in the video. So that's, can't really zoom out anymore. We'll just leave it like that.